Welcome back to another video on my series on special relativity. So today we're going to be trying to put it all together and do what we set out to do in the first place, and is show that t prime in general is a function of x and t of the unprimed system. In the last video we showed the length contraction factor, this gamma here. We showed basically how x prime is this factor times L. Right, so this is a length contraction factor here. Today we're going to be using all of these definitions that we've come up with over the past several videos to get this expression. Okay, so the first thing we're going to do is we're going to say t prime equals beta t, and we're going to substitute in L equals x minus vt. That's the first thing we're going to do. So we get minus vx over c squared minus v squared. And then we get minus a minus, which is plus v squared t. So it's clear I just put in this guy. And then over c squared minus v squared. I'm going to get this whole thing under in the same denominator. So we're going to do t c squared minus v squared. This is all going to be all over the same thing, minus vx plus v squared t, all over c squared minus v squared. Then we see that there's going to be some stuff cancel for us, which is nice. So we get c squared t minus v squared t minus vx plus v squared t all over c squared minus v squared. The v squared t drops out. Okay. And what I want to do next is I want to actually take out a c squared. So I'm going to have b take out a c squared. And we know that on bottom here is c squared minus v squared. Okay, so let's do some factoring. The t already had a c squared in front of it, so that's fine. The vx did not, so we're going to have to do vx over c squared. And what we'll find is that if we take beta, actually let's write it out. Let's do it here. Beta, what's beta? Well, beta is square root c squared minus v squared over c, and then we have c squared and then c squared minus v squared, and then the same thing, t minus vx over c squared. We lose the bottom c, and then we get the half. Square root comes down on the bottom, so we get c over square root c squared minus v squared of t minus vx over c squared. Okay, and what is this thing here? Well, that's 1 over, it's easy to see that that's equal to 1 over beta. And 1 over beta, as we already defined it, is gamma. So remember what we're solving for here. We're solving for t prime. So now we've shown that t prime is equal to gamma, which is actually our length contraction factor, times t minus vx over c squared. And this is the standard Lorentz transformation notation you will see. Let's write all of the coordinate transformations out now that we have them all. So x prime is equal to gamma times x minus vt. We showed that in the previous video. I've already mentioned that y prime is equal to y. Remember, we're traveling in this direction. A photon that's flashing, in the vertical component does not get changed by this coordinate transformation. Okay, this vertical distance is the same for both observers, and it's exactly the same. And then also we get z prime. Oops, let's do it in blue. We get z prime equals z. So there you have it. It took several videos, but here are the Lorentz transformation. This is a coordinate transformation. And I'm thinking about doing some more videos on showing some properties of this coordinate transformation. Obviously, we derived this whole thing assuming a constant speed of the object. This is special relativity, right? This is what Einstein called special relativity, the special theory of relativity. But there are some properties of this transformation that Einstein generalized to basically nature, he said. He said there are certain things that I think we can look at this and say these things will be invariant under coordinate transformations, and that the laws of physics must be consistent under coordinate transformations. So I'm thinking about doing some videos on that and moving on in the topics. But please let me know what you think in the comment section, and feel free to like and subscribe, and I will see you next time.